Okay, so there are 30 seconds left, and the AtCoder beginner contest 187 will begin. Let's wait for today's problems. Okay, here they come. Problem A, large digits. If they are equal, print SA. Okay. Okay. Python. What's wrong? Greater of SA and SB. Okay. Now, problem B, gentle pairs. X, Y plane. Have endpoints numbered 1 to n. Point I is xi, yi. The line passing through point I and point J has a slope between -1 and 1. Okay, we just need to calculate the slopes. I is smaller than J. xi and xj are all different. We'll generate some test cases. Okay, problem C, one set. There are n strings. Each of these is a non-empty string. Determine whether there exists unsatisfied string. Si and the length. Okay, so it should be an easy problem. Add 0 or 1 ben at the beginning. So we just need to check we need an unordered map. We need unordered set. Zero or one. Ben. So where did we go wrong? There must be some issue about the namespace. Okay. So problem D, choose me. Okay. I will not omit using namespace std this time. Okay, so we are supposed to need to use long. So this should be an easy problem. We just need to sort the tons according to the delta. To count the sum of A and B. So after speech, the pro-Aoki voters will also vote for Takahashi. So we need to include algorithms. To sort. According to their second value. So No, according to the first value. So we can just use the default compare function. So we need to compare according to the first value. So if SA, that means people supporting AOKI, is still already smaller, then we just need to otherwise we will finally create a sample file. Test it. Nope. So we're outputting 2 instead of 3. What's wrong here? After changing 2, 6. So, okay. If it does not make a speech in some town, the pro-Aoki voters in that town will vote for Aoki, and the pro-Takahashi voters will not vote. Okay. So, we need to change our sorting. So, 1 vote will bring change. So first, do that. So, okay, so we need to also use long here. So delta is actually 2 times p dot first plus we will not use r begin and r end since we already defined that in the in the compare function. And here, so let's say we'll lose, yeah, second, check, nope. What? Still not right. Oh, yes. At first, SB equals 0. Yeah, should be correct now. Okay. Now let's move on to problem E. Touch E.cc. Let's move on to problem E. So we have a tree with n vertices and n minus 1 edges. We have a tree. Okay, we have a tree. We have a tree, and there are q queries, which vertex v reachable from vertex ai, result visiting vertex bi by traversing edges. Replace cv. So v reachable from vertex AEI. Okay, so each time we will have an edge, and for each kind of operation we will need to change all the nodes on one side. So actually we can store global additional value and make the both type of queries the same. Yeah, we can do this. We can do this. So we will need to do some recursion. this is an undirected tree. This problem is not that difficult because we do not need to query the value of the nodes during our modifications. So we only need to query the value of each node at last. So we can just use some lazy propagation, and in the last run we will push down the values. So let's first build a tree. So we'll suppose number 1 to be the root. We'll also need to use long in this problem. Yes, build tree. Parent. EI. So we also need to store the edges. Because we will need to store the parent. Yes. We will also need to store the lazy value. Build a tree, and we will need a global value. Now we need to input Q. T and E and X. If T equals 2, we will swap U and V. Swap U and V. And now suppose we are going always go from U to V. So the edge from U to V is bent. The edge from U to V is bent now, and we are starting from U. We are starting from U. So there are two cases. In one case, U is parent of V, and in the other case, V is parent of U. So if V is parent of U, we just go down. It's an ordinary case, so we need to handle. If U is the parent of V, then we need to go up from U instead of go down to the subtree. So we will need to global lazy add O value. So the top half and the bottom half are both added x now, and we need to subtract x from the bottom half. So x equals minus x. Then parent V equals U. Then we will go from V, go down. So we will swap U and V again. And now we will go from U. So yes. And finally we need to push down. Push down. Put the answer. Okay, need to test. See if we can get it right with the first attempt. Okay, we passed the test. Okay, we passed the main test. And now we'll move on to the last problem. That is problem F. Touch f.cc. So we have a graph with n vertices and m edges. The vertices are numbered 1, 2 to n, and the ith edge connects AI and BI. Vertices A and B belong to the same connecting component. There is an edge that directly connects vertices A and B. So we need every kinetic component to be a complete graph. Find the minimum number of kinetic components. Okay. Actually, we can check each subset. Yeah, it's not that hard. Just need a full array. So here we have all edges are different. Yeah. So we will use 0 index here. So this is a bit mask dynamic programming problem. Yeah. We will need to do some pre-calculation. Eighteen is a subtle number. So if we enumerate each subset, see if it is possible. We will need equals this is sort of big, sort of large. We'll have 8. Then the second part, to enumerate each subset. Each subset. Do subset dp, which will cause us okay. Maybe you can have a try. check whether we will pass, whether we can pass the time limit. So we are outputting. So what's wrong? Oh, it did not input. Okay, it takes 1 second, which should pass. Okay, we passed all the problems. The rank is not very good, 191, and I have 1 penalty, so the rank may still drop a little more. Okay, now let's look at today's problems. We will start from problem A. So in problem A, we need to compare 2 numbers, A and B. Instead of compare them directly, we need to compare their sum of digits. So, for example, A is 123 and B is 243. We will not compare them directly. Instead, we will compare 1 plus 2 plus 3 equals 6 and 2 plus 4 plus 3, which equals 9. So here we will output the larger of these two instead of these two. In this case, we will output 9. So in the code, we just transform the number into a string and then map each digit into an int and then get their sum. Then we do the compare and output the larger one of the two. Okay, now we'll move on to the next problem, problem B. So in problem B, we have 1000 points and each is xi, yi, xj, yj, and we know that none of these points have the same x value, so there will not be a vertical line if we connect any 2 points of them. Now the problem is asking us how many pairs there are that if we connect them, we will get a line and we can calculate its slope, and we want the absolute value of the slope to be no larger than 1. Since there are only 1000 points, we can just enumerate all the pairs and calculate the slope. Here, instead of calculate the slope, which might be a double or float instead of an integer, we can just compare their dx with dy. So we can translate this into the absolute value of dx is larger than the absolute value of dy. So this will be an integer comparison, which will be simpler. Now let's go to problem C. So this is actually a comprehension problem. So it's not hard to implement. You just need to understand what the problem says. So it says that there are some strings. They are no longer than 10. So they are all very tiny strings. We have like AB, Ben AB, C, Ben C, CD, D, and so on. So now the problem asks whether there is a string consisting of lowercase characters only. Whether there is a string. The string itself can be found from these strings. And also, when we add a pen in front of the string, BandS can also be found from these strings. So we just need to implement this with 2 sets. We use 2 sets. So in one set, in my code, I named it clean. We store the strings that without a band. So here we store AB, C, CD. and D. And in the other set, which we call it band, meaning that there should be a band in front of the strings. We store the strings here with a band in the front. So we store A, B, and C. Then we simply enumerate all the strings in one set. Or if you use Python, you can use something like intersection to get the intersection of these two sets. So if their intersection is an empty set, there will be no string that can suit both sets, so we will just output satisfiable as the problem requires. Otherwise, we can choose arbitrarily from the intersection, and each string of this intersection will be a valid answer to this problem. Okay, let's move on to problem D. Show the solution here. So let's first look at the problem. So the problem says that there are several towns, and there will be an election. So there are two people, A, we call them A and B, and in each town, there are A1 people supporting A and B1 people supporting B. In town 2, there are A2 people supporting A, while B2 people supporting B. But here we need to be careful, because the problem says that if we do not make a speech in a town, then AI people will vote to A, while no people will vote to B. However, if we make a speech, then no people will vote for A, while AI plus BI people will vote for B. So the delta here is actually 2AI plus BI. Since the problem asks us to find the minimum number of speeches we need to make so that B can win the election, we just sort all the towns according to their value of 2AI plus BI in the descending order. Yeah. So we'll first make a speech at the town with the largest 2AI plus BI. Of course, if the sum of B here, so if we make no speeches, B cannot win, because no people will vote for him if we make no speeches. So the answer must be a positive number. Then we just try. We try each town according to our sorted sequence, and we will make the changes according to these rows and find if we make the speech at this town, whether B can win. So if B already wins, we will stop making more speeches and we are done. Now let's move on to problem E. So at first sight, E looks a bit scary because we need to do a lot of modifications and we need to query the values. However, one thing is very important here because we only need to query the value. So the sequence is like this. We modify, 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 and there are in total Q modifications. Then after all these modifications, we do the query. Yeah, we can consider it to be query, 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 and we need to do n queries in total since we have n nodes and we need to get the value of each node. So now this makes the problem easier because we will not make a query between two modifications. That means we do not need the intermediate statuses. We only need the final states. So let's look back at the original problem. We have a tree. So without loss of generality, we will make 1 the root. And we can do a depth first search to get the parent of each node. So we will make it a directed tree. And these are the edges. So there are two types of queries. In the first type of query, for an edge EI, which is AI, BI, we want to find that all the nodes AI can go to without passing BI. Suppose here, if this is A, and this is B. Then this point, and this node, they are invalid because we need to pass B to get to these nodes. However, A itself and this node, they are valid because we can go to them without passing B. So in this case, we can find that these nodes are exactly the nodes of the subtree with A as its root. But there are another case. So there are type 2 modifications in which we will consider the edge inversely. In this case, we want to find the nodes we can go to from B without passing A. They will be these nodes. And in this case, they are not the subtree with the root, with B as its root. So this makes it harder. But since we only need the value of each node at last, we can just do a flip. So suppose we want to modify these nodes which are not a subtree. We want to plus x to them. Then we can do it inversely. We can actually add x to all the nodes. Then we will add minus x to these nodes. And they just form a subtree. And for a subtree, we do not need to go down to the leaves, and we just need to store the value at its root. In this case, we will store minus x at a. So this is a bit like the lazy propagation in segment trees. Then after all the modifications, the same tree here. After all the modifications, we will have a global lazy value. Which will be added to every node. Then at each point, each node, we will have a lazy I. Which means the value that needs to be added to the subtree with this node as its root. So this is lazy 1. So here maybe we have lazy 2, lazy 3. So how do we find the values of each node? For this node, we just get its value from global lazy plus lazy 1. Then we will push down lazy 1. We'll push down to its children. So for this node, its value will become lazy 1 plus lazy 2 plus global lazy. And for this node, its value will become lazy 1 plus lazy 3 plus global lazy. And we just do this recursively, and we will solve this problem. Okay, this is problem E. Now the final problem, problem F. So here we have a graph with n nodes and n edges. So n nodes and n edges. And here we can see that n is small because n is no larger than 18. This kind of indicates the usage of bit mask dynamic programming. And we'll look into it later. So the problem asks us to find the minimum number of connected components we can get. So we want the number of CCs to be the minimum. And there is a constraint that for every two nodes in a CC, for example U and V, they must be connected directly. So there must be an edge from U to V. So the edges are undirected, so we will use, there must be an edge between U and V. So what does this mean? It means actually we need all the connected components to be a complete graph. So if there are 3 nodes, they must be like this. If there are 4 nodes, they must be like this. So now actually we can check if a subset of the n nodes can be a valid connected components just by simply enumerating. So suppose we have a subset with 1, 3, 5, 7, and we need to check if they can make a complete graph. So we just check if there is an edge 1, 3, 1, 5, 1, 7, 3, 5, 3, 7, and 5, 7. We check if these edges all exist. So in this problem, to check the existence of edges quickly, we will store the graph with an adjacency matrix instead of adjacency lists, which we will use in most cases. In this case, we need an adjacency matrix. So this is the fastest way to check the existence of an edge. So in this cases, in this problem, in the worst case, we need to check (18/2) subsets, and for each subset, the worst time is 18 times 18, and this is smaller than 100 million. Then after getting this, we will have a Boolean array. We call it can. Then for any subset, we can know if we can make it or we cannot make it. Here we will represent all the subsets with a binary number. So for example, the subset 1, 3, we will use 1, 0, 1 to represent it. Now after getting the array of can, we can just do a subset dynamic programming. So here we use DPS to represent the minimum number of connected components we can get from the subset of S. So first case, if can S equals true, then we will have DPS as 1, because we can just use all the elements of this subset. And in the second case, if can S is false, it means we need to split this subset into at least 2 smaller subsets. So actually here we need to enumerate the subsets of a subset. If we do it naively, we will need to make 2n/2 times n/2, which equals n/4, and in this case 18/4, which is too large. However, we have a smarter method to enumerate the subsets of a subset. That is, you can see it in the code. we can enumerate it like for int s equals larger s minus 1 and is s equals s minus 1 larger s. We can enumerate the subsets of the subset in this way. And this will yield a time complexity of n over 3. And in this case, 18 over 3, which is more enough for us to pass the time limit. So why does this trick work? Because it will exclude the invalid cases. So there are some cases that a number is smaller than large s. However, it is not a subset of S. And by enumerating the subsets like this, with the AND operation, we can ensure that all the numbers we enumerate are valid subsets of large S. And in this case, we can have a complexity of n over 3. So after the enumeration, we will update dps with the minimum of dp sub plus dp s XOR sub. So this problem is done. You can look at the code for more details. And now we are finished. Have you enjoyed today's contest? Have you enjoyed today's problems? If you have, then I'll be very appreciated. Thank you for watching and see you next time.